Hello students, in this video I am going to talk to you about deduction of a molecular structure from the given proton NMR data and molar mass. Okay, so the question at hand, we have been given a compound that contains only carbon and hydrogen, so it's an hydrocarbon. It's a molar mass of 148 and the 1H NMR is also given below. See, if we look at the 1H NMR, there are actually, we can see from the top, okay, overtly we can see that there are total of 5 peaks, but actually there are 6 peaks which I'll explain later. So we can see actually, okay, 5 signals there, okay, that we can see with our eyes, but actually there are 6 signals over there which I'll explain later. Okay, now let us look at the downfield part, or the leftmost part of the NMR around the aromatic region, which is between 6 and 8 ppm. So around 7 ppm we see 2 peaks, okay, 2H peaks. We can see the total of there are totally 2H plus 2H 4H aromatic protons. Now what does that tell you? That tells you that this is a disubstituted benzene. Why is that? See, totally a benzene ring has got 6 protons. So if only 4H protons are showing in the aromatic spectrum, which means 2 of those positions are substituted, right? So this is a disubstituted benzene. Moreover, the splitting patterns, there are 2H doublets there, A and B, signals A and B. So what's happening there? This kind of a splitting pattern, okay, is only found in para disubstituted benzene. So A and B are mutually splitting each other as doublets. Okay, that's what's happening. Now we move a little bit further upfield. Okay, we come to around close to between 2.5 and 3 ppm. We see 2 peaks C and D. Okay, signal C and D. C is a 1H septet. Okay, and D is a 2H quartet. Okay, now what does the chemical shift tell us? The chemical shift tells us that these are benzylic protons. What are benzylic protons? Benzylic protons are those protons attached to a benzylic carbon, a carbon that is attached to an aromatic ring. So that's called a benzylic carbon. So these are benzylic protons. So which means, once again, we know that from the aromatic part of the spectrum, we know that this is a disubstituted benzene, para disubstituted benzene. So which means these two benzylic protons are actually para to each other, right? Okay, so benzylic carbons are actually para to each other. So these protons are attached to those carbons there. Okay, so now what does the septet tell you? HC is a septet, which means HC, the signal C, is flanked by 6 protons. Okay, 6 equivalent protons. So very likely this could be 2 methyl groups. So which means HC could be part of an isopropyl system. Okay, what does HD tell you? HD is a quartet. So which means it has got 3 equivalent protons in its neighborhood. So which means there could be a single methyl group next to it. So which means HD is part of an ethyl group, right? So that's what is established now. So which means we can now picturize this aromatic ring, 2 substances which are para to each other. On one side could be an isopropyl system, on the other side could be an ethyl system. Okay, so let us confirm this. Okay, we see a 9H peak there, and that looks like a bunch of multiplet further upfield at around 1.2 ppm. Okay, so now actually this looks like a single signal, but actually there are 2 signals here, E and F. Why would that be? See, we know that HC is a septet, so it has got 2 methyl groups on its either side, right? So that is a signal over there, E, and also HD is a quartet, so it has got a single methyl group next to it. So that is the signal over there, HF. Okay, so E and F literally come around the same chemical shift, so they overlap each other, so they look like a bunch of multiplets there, which is not the case, right? So this is actually a peak. Okay, 2 peaks actually looking like one. Okay, all right, so let us summarize this, what we found. Okay, there are 2H doublets, HA and HB, adding to a total of 4H protons in the aromatic region, 6 to 8 ppm. 4H protons indicate that this is a disubstituted ring, and the splitting pattern indicates a para disubstituted ring. Okay, both HA and HB mutually split each other. Okay, the peak HC and HD at 2.8 and 2.7 ppm precisely are very likely benzylic protons. Okay, and these benzylic carbons are para to each other. Okay, HC is a septet while HD is a quartet, which means HC has 6 equivalent adjacent protons. HE, signal HE, which is nothing but 2 equivalent methyl groups, while HD has 3 equivalent adjacent protons. HF, signal HF, which is very likely a single methyl group. Okay, so the 9H peak at 1.2 ppm is actually a combination of those 6H HE as which is actually a doublet, and a 3H HF, which is actually a triplet. Okay, they are overlapping each other. Okay, now 9H peaks are shown in NMR spectrum of also tertiary butyl groups, but it comes across as a singlet. Okay, it doesn't come across as a splitting pattern. Okay, like what we see here. So that can be eliminated, right? So with all this data put together, we can say that the given structure is 1-ethyl 4-isopropyl benzene. Okay, so look at this, the way the protons have been labeled. You can see HD, HF, HD and HF split each other, mutually split each other. HD will be a quartet, HF will be a triplet, right? HB and HA mutually split each other in the aromatic region as a doublet and doublet, right? You can see 2H doublets, and then HC is a septet because it is split by 6 He protons, and He will be a doublet. Okay, so the thing is, moreover, between HB and HA, HB will be further upfield compared to relatively upfield compared to HA. Why is that? Because see, HB is ortho to the ethyl group, while HA is ortho to the isopropyl group. Okay, and ethyl group has got a greater plus I effect. Plus I effect means it increases the electron density, okay, on its ortho position, and therefore HB will be relatively upfield compared to HA. Okay, so moreover, this molecule also satisfies the molar mass of 148. So all this put together, our compound is 1-ethyl 4-isopropyl benzene. Thank you and have a nice day. Bye.